Hello friends, I am Snehal and we are studying physics. In one of the earlier lectures, we had just stated the Gauss law. Today we are going to see the Gauss law in more detail. So let us recall the statement of the Gauss law. It says that the electric flux due to electric field through any closed surface is equal to the sum of charges enclosed by the surface divided by epsilon naught. And epsilon naught is obviously the permittivity of free space. Then the law can be represented mathematically like this. The electric flux we denote it by phi, and it is equal to the sum of all the charges qi, where I runs from 1 to n, that sum divided by epsilon naught. Now let us try to understand the Gauss law, and for that let's try to understand the flux. So consider this rectangular pipe and suppose some liquid is flowing through this pipe. V bar is the velocity of the liquid, and we are interested in finding out the flux of this liquid through this surface. So let's name it ABCD. Now flux of the fluid flowing through any surface is defined as the amount of fluid passing through that surface per unit time. So flux of the liquid through ABCD, the surface ABCD, is equal to amount, that is the volume of liquid flowing through ABCD per unit time. Now suppose the fluid and that area ABCD, they are perpendicular to each other. So I will call area of this surface as A perpendicular because it's perpendicular to flow of fluid. Now we have to find the volume of this liquid flowing through this surface per unit time. So suppose at some time t, the fluid was at this surface, and in some time, let's say t plus delta t, in time interval delta t, the fluid moves from here to, let's say, here. So the distance covered by the fluid is delta x in time delta t, and that's why we can say V is equal to delta x divided by delta t. Then therefore the volume of this fluid flowing through this surface is equal to volume contained in this much region, and clearly that should be equal to the area of the surface multiplied by this length. So it is A perpendicular multiplied by delta x, and we want volume per unit time, so that's why we should divide by time, and then this delta x divided by delta t gives us the magnitude of velocity. So flux we denote by phi. So flux of this fluid through this perpendicular surface is equal to product of area of that perpendicular surface multiplied by the volume. So this is for the specific case of the perpendicular surface. Now let's imagine some other surface. So for an example, let's imagine a surface like this, So this surface, let's name it CDEF. It is inclined to the perpendicular surface at some angle theta. Now we are interested in finding out the flux of the fluid through this inclined surface. So intuitively we can think that the flux through this surface and that surface should be equal, though the the areas of the surfaces are different. See, this CDEF has larger area compared to ABCD, but still the amount of fluid flowing through these two surfaces is same. So can we relate the area of CDEF to the flux through the CDEF? So let's try to do that. Now let us redraw these surfaces here. So this one is ABCD, and this is the other one, CDEF, and let's join this side. So this length I will call L perpendicular, and this length I will call L, and the breadth I will call B. So now let's find the area of ABCD. So the area of surface ABCD is A perpendicular, and that is just this length multiplied by this breadth. So it is L perpendicular multiplied by B. And similarly we can find the area of CDEF. So area of CDEF let's call it just A, and that is equal to this L multiplied by the B. Then we'll divide these two areas, area A perpendicular with area A. So A perpendicular divided by A gives me L perpendicular multiplied by B divided by L multiplied by B, and this B gets cancelled. And if you see in this triangle ADE, if you look at this angle theta, then cos of this angle, the cos of theta, is L perpendicular divided by L. So this L perpendicular divided by L is cos of theta, and hence we have A perpendicular equal to A multiplied by cos of theta. And we can substitute the relation we got in this formula. So we get flux through A, that is the area of CDEF, phi equal to, I will substitute A cos theta in place of A perpendicular, so it is A cos theta multiplied by V. So this is the relation for flux. Now we are going to represent area as a vector quantity, and you will see that the things fit very nicely. So let us consider this surface ABCD, So the area of this surface ABCD, we called it A perpendicular, and since we are considering this to be a vector quantity, it has to have a direction, and the direction of area vector we take along perpendicular to the plane of area. So this vector represented by this arrow is A perpendicular bar. So similarly, let's consider this surface CDEF. It is inclined at an angle theta to this ABCD. So this is CDEF, and magnitude of area of CDEF was A. Its direction is along normal to the plane of CDEF. So it's like this. So this vector is A perpendicular bar. Then let's consider fluid coming in from this direction. So the velocity of fluid is v bar. It is in horizontal direction, same as that of direction of A perpendicular, and we calculated the flux flowing through A perpendicular in terms of this A perpendicular, which was phi equal to magnitude of this area multiplied by the magnitude of velocity. So similarly, here too, let's consider the fluid coming in this direction. So v bar is the direction of velocity. So I can represent this velocity vector like this. So since this angle is theta, the angle between ABCD and this CDEF, the angle between the perpendiculars should also be theta. So this angle should also be theta. Now we had calculated the flux through this surface as the magnitude of this area A into V multiplied by cos of theta. So this is flux through CDEF, this inclined area. Now we can represent this flux as the dot product between this area vector and velocity vector. Recall that dot product A bar dot V bar is equal to magnitude of A multiplied by magnitude of V bar multiplied by the cosine of the angle between these two vectors. And what about this case? So in this case, the angle between these two is 0. So here also we can represent this as A perpendicular bar multiplied by V bar, the dot product, and it is magnitude of first vector multiplied by magnitude of second vector multiplied by cos of the angle between two, which is cos of 0, and we know that the cos of 0 is 1. So this is just A perpendicular multiplied by V. So in this way, if we consider an area to be a vector quantity, then we can represent the flux of this vector, let's say V bar, through this surface area as the dot product between the area vector and the vector whose flux we are finding out. Alright, now next thing we need to know in order to understand the Gauss law is solid angle. So let us recall the plane angle. Suppose this is a circle, this is center of the circle, and let's consider this arc AB. So angle subtended by the arc AB at the center, let's say it is theta. How do we measure theta? So theta is equal to arc length divided by radius. Suppose the arc length is S and radius is R. So theta is equal to S divided by R. What would be the angle subtended by this complete circle, by the circumference of the circle at the center? So I will call it theta max. This is the angle due to complete arc length of circle or the circumference of circle, and it should be equal to the circumference divided by radius, that is 2 pi r divided by r. So this r gets cancelled and we get theta max equal to 2 pi. Okay, now imagine that instead of circle we have some other closed curve like this. So what is the angle subtended by this closed curve at this point or at any internal point? So we can draw a circle surrounding that point, and we can say that the angle subtended by this closed curve is just equal to the angle subtended by the circle, and that should be equal to theta max, which is 2 pi. Okay, so this was the two-dimensional angle. Now let us consider what we call a three-dimensional angle or a solid angle. Now to define a two-dimensional angle, what we need is arc and the radius. For three-dimensional angle, we need a surface area. So let's consider this surface area. Let's say it is ds. And now we know that an area is a vector quantity. So the direction of area is perpendicular to plane of area. So this is the vector ds bar. Now let's consider this point O and let's join ds with the point O. This is R. And suppose that ds bar is in line with this R. What it means is that the plane of area is exactly perpendicular with the R. Now the solid angle is what we get when we join all the points of periphery of this ds with this point O. So you can imagine when we join all such points at the periphery of ds with O, what we are going to get is a cone-like thing. So that cone is the 3D angle and it is called as the solid angle. The question is, how do we measure this cone or the solid angle? So the solid angle subtended by ds at O is defined as the surface area, the magnitude of surface area divided by the perpendicular distance squared. So we have denoted the solid angle by d omega, and when we measure the solid angle like this, the unit of such measurement is steradian. Now this surface ds, the plane of this surface is exactly perpendicular with R. What if we have a surface whose plane is not exactly perpendicular to R? How to find the solid angle? So let us consider such a surface. Before that, let me redraw this here. So this is ds I will call this one ds perpendicular. So this is ds perpendicular bar, and the solid angle due to this is ds perpendicular, the magnitude, divided by r square. So this is that ds perpendicular, and suppose this is the point O where we have to find the solid angles. Now let's consider another surface and let's call it ds. So this is that surface, and it should be clear from here, from the diagram, that the solid angle, the cone subtended by ds perpendicular and this inclined surface ds, they are same. Okay, both subtend the same amount of solid angle or same amount of this cone. So how to express this solid angle in terms of this surface? So we have a clue that the angle between these two is theta. So angle between perpendicular to ds, ds perpendicular, and perpendicular to this ds, that angle is also theta. And we have already written that ds perpendicular is equal to ds cosine theta, or a perpendicular equals to a cos theta, to be particular. So we can represent the solid angle d omega in terms of ds as ds cos theta divided by r square. Since ds perpendicular is equal to ds cosine theta. So this is how we express the solid angle in terms of the area. Now the question is, what would be the maximum solid angle subtended by a closed surface at any point? So for that, let's consider this sphere, and we know that the solid angle subtended by a surface area at any point is equal to the surface area divided by r square. So in this case, the total surface area is equal to 4 pi r square, the surface area of sphere, and divided by, we have r square. So this r square and r square, they get cancelled, and we get maximum solid angle, which we will call the omega max, is equal to 4 pi. So omega max, the solid angle subtended by a closed surface, no matter what closed surface, any closed surface will subtend the solid angle omega max equal to 4 pi at its interior region, at a point in the interior region. And how can we find that total solid angle? So we can have this surface as a part of a big closed surface like this. So this much surface subtends solid angle of d omega. So if we consider such small surfaces over this entire closed surface, then the sum of those solid angles subtended by all those small surfaces will be equal to the total solid angle subtended by the closed surface. Okay, finally, let us try to prove the Gauss law. So let us consider this random closed surface, and suppose there is this charge q somewhere in the interior region of this closed surface. We know that the electric field due to the charge q at distance r away from it is given by 1 over 4 pi epsilon naught multiplied by q divided by r square. And the electric field is in radial direction. So to show the direction, we use this unit vector in radial direction. So this is our electric field vector E bar. Now let's consider some surface, small surface ds. So ds is some small surface, and we know that an area is a vector quantity. So ds is actually the surface area. This is ds bar along direction normal to the plane of ds. The distance of ds from q is, let's say, r, and therefore the electric field at ds is in radial direction. So this is the electric field vector. Now suppose theta is the angle between electric field vector and ds bar. So now we know how to find a flux of vector. So for V bar, for this flow of fluid through this surface area, let's say A bar, the flux was A bar dot V bar, that is A into V into cos of theta. So here the flux due to the electric field vector on same grounds should be equal to E multiplied by ds multiplied by cos of theta. So flux of E bar through ds, let's call it d phi because we picked very small surface area. So that flux should be equal to E bar dot ds bar, the dot product between vector and the surface area. So it is A ds into cos of theta. Now therefore the total flux through this total closed surface is sum of the flux due to all such surface areas. Through all such surface areas. So the total flux through the closed surface I can say phi is equal to the sum of flux through each and every small region ds taken over this closed surface, and that's why the total flux should be equal to the continuous sum, and therefore we take this integral. So it is integral of d phi, that is integral of E ds into cos of theta. Now let's substitute the E. So we know that E is equal to the magnitude of electric field, which is 1 over 4 pi epsilon naught into Q divided by R square. So let us substitute it here. Multiplied by ds into cosine theta. Now let's identify what are variables and what are the things which are constant. So Q is constant, 4 pi is a constant, epsilon naught, which is permittivity of free space, it is another constant. So we can take them all outside of this integral. So we have Q divided by 4 pi epsilon naught. Then what we are left with is ds cos theta divided by r square. Now this is not a constant, since the magnitude of ds can change. The angles can change according to the direction of electric field and the area vector, and distance of the areas taken over this closed surface is also not a constant, since distance here is different from distance here. So these things are variable. Now recall, we defined the solid angle due to the surface ds by this thing. So this thing is just the solid angle due to this surface subtended at this point. So this is just d omega. So we have q over 4 pi epsilon naught to integral of d omega. That's pi. Now integral of d omega is just sum of the solid angles due to all such surfaces taken over this closed surface, and that should be equal to the total solid angle subtended by this closed surface. So that integral is solid angle, a total solid angle subtended by closed surface, and we have just found that the solid angle should be equal to 4 pi. So we can substitute it here. So we get pi is equal to q divided by 4 pi epsilon naught multiplied by 4 pi. So this 4 pi and 4 pi gets cancelled, and we have pi equals to q divided by epsilon naught. Okay, now this is flux due to one charge q. So what if there were n number of charges? So I can say for n charges, q1, q2 up to qn, the respective flux is phi 1 equal to q1 divided by epsilon naught. For one charge we proved this. So phi 2 should be equal to q2 divided by epsilon naught, and so on. So the total flux due to n charges let's say phi total should be equal to phi 1 plus phi 2 plus up to phi n. It is just sum of the fluxes due to individual charges q1, q2 up to qn. So this is equal to q1 divided by epsilon naught plus q2 divided by epsilon naught, and so on up to qn divided by epsilon naught. So that means phi total is equal to sum of charges q1 plus q2 plus up to qn divided by epsilon naught. So it is just q1 plus q2 plus up to qn divided by epsilon naught, and that means that it is just summation of all the charges qi, where I runs from 1 to n, divided by epsilon naught. So this is our required result. So this is the proof of the Gauss law. So let's recall the statement once. The electric flux due to the electric field through any closed surface, which is phi, or phi total, is equal to sum of the charges enclosed by the surface. So the charges which are inside there in the surface, the sum of all those charges divided by epsilon naught. Okay, so we have learned the Gauss law of electrostatics. It is very powerful law. So next time we will apply Gauss law to find out electric field for various situations, and we'll see how powerful it is. Thanks for watching.